Hello everyone, welcome back. Last time we finished up looking at two-dimensional kinematics. Remember, kinematics was the area of physics where we're looking at motion, we're analyzing motion, but we're not talking about why an object has the motion that it does. We're only talking about describing that motion. What we're going to do today, what we're going to start today and continue for quite a while, is start looking at a different area of physics called dynamics. We're moving from kinematics to dynamics. Dynamics is the area where we start to describe why the objects have the motions that they do, what's causing the objects to move the way they are. The combination of the two areas of kinematics and dynamics is the area of mechanics. Now this brings us to our next section, section number 4, which is entitled Forces and Newton's Laws of Motion. Back in the 16 and 1700s, there was an individual, an absolutely amazing individual by the name of Sir Isaac Newton, and he revolutionized the area of mechanics. He wrote a book that we refer to now as the Principia, Principia Naturalis. He wrote the Principia and totally revolutionized the area of mechanics. Three parts that we are going to look at are what we now refer to as Newton's laws, three laws of motion. And what we're going to do today is look at them one at a time. They are sometimes referred to actually by their number. So there's Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. And we're going to look at them one at a time, and that's what we're going to do today. To understand Newton's laws, we need to introduce a new concept that we haven't talked about before, and that is a force. Qualitatively, we can think of a force as a push or a pull. So anytime you push on something or anytime you pull on something, you are applying a force. I can push on this wall, I could push on this apple, I could push on it, I could pull on it, I could pull it upwards like that. Those are forces. I am applying a force on the wall, on the apple, something like that. So anytime you apply a push or a pull on something, that's a force. Now, there doesn't have to be any motion involved. I can push on this wall, and even if the wall doesn't move, I'm still applying a force. So no motion is necessary for a force. Now, we can sometimes categorize forces in two different kinds. There are what we might call contact forces. So in order for me to push on this apple, I have to have a contact between my hand and the apple to push on it. I can't push on the apple without touching it. The air might be pushing on it a little bit, but my right hand is not pushing on the apple. My left hand is pushing on it, but I'm not pushing on it with my right hand. So in this case, there has to be a contact involved between my hand and the apple for that force. There are other forces where contact is not required. For example, the earth pulls on the apple and pulls it downward because of gravity. So gravity is not a contact force. It's what we refer to as a field force. So the apple falls because it is in a gravitational field. We'll actually talk more about that later on. Another example is, for example, the magnetic force. So I have a magnet here, and here I have some paper clips, and if I bring the magnet close to the paper clips, it attracts the paper clips and pulls them up. Without touching them, it pulls them upward. So it exerts a force, pulling the paper clips up, like the earth pulling the apple down. So magnetism is another example of a force, a field force, where contact is not necessary. So it doesn't matter whether we're talking about a contact force or a field force, Newton's laws are still going to apply. Now, something else to keep in mind is, what about the direction? Well, if I push on this apple, if I push on it this way, one thing happens. If I push on it up, something else happens. So the direction of forces are important because the direction of the force will help determine what's going to happen to the object. So what do you think? Force must be what kind of a quantity? If direction is important, it must be a vector. So when we want to refer to a force, we will often use the letter F, sometimes uppercase, sometimes lowercase. And when we want to refer to the vector nature of the force, we will put a vector sign on top. So, in general, forces are vectors. We'll sometimes refer to the magnitude of the force, but when we refer to a force, we're talking about a vector quantity. Okay, excellent. So, let's now start looking at these three laws of Newton, Newton's three laws of motion, and we'll look at them one at a time. Newton's first law, also referred to sometimes as the law of inertia. It states, an object continues in a state of rest or in a state of motion at a constant speed along a straight line unless compelled to change that state by a non-zero net force. So let's look at this. What does this mean? So in a state of rest, that means stationary. That means zero velocity. A state of motion at a constant speed along a straight line. What does that mean? Constant speed along a straight line, that's constant velocity. So this is basically stating in a state of rest, zero velocity, or constant speed along a straight line, non-zero velocity. So basically this is just saying a constant velocity. An object continues at a constant velocity unless compelled to change that by a non-zero net force. Now, what do we mean by a net force? Net in this case means a total, or the sum of all forces acting on an object. So imagine we've got some object with a bunch of forces acting on it from all sorts of different directions. Say a force this way, a force that 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 way, whatever. There's a whole bunch of forces acting on this object. We could call these F1, F2, F3, etc., as many forces as we want. The net force is then equal to the vector sum of all of these individual forces. F1 plus F2 plus F3 plus etc. Keep in mind, this is a vector sum. Now, if we have an object that has a force, let's say pointing to the right, and an equal but opposite force pointing to the left, what is the net force? The net force would be zero, because these two forces, when we add them as vectors, give us zero. Remember, adding vectors, you put them head to tail. This would give us zero net vector, zero net force, so the net force in this case would be zero. If there is a zero net force, in other words, if there is no force, no net force acting on the object, then we have the object maintains a constant velocity. So what does that mean? That means if, kind of ignore my hand for a minute, if an object is moving and there is no net force acting on it, it's going to just keep moving at a constant velocity in a straight line, and it's just going to keep doing that, moving along in a straight line. Imagine this is like out in outer space or something like that. Something that's moving is just going to maintain a velocity and move along in a straight line. What would cause it to change its velocity? Well, we have to have a non-zero net force. This is actually a very, very different idea than the prevailing physics of the time, the Aristotelian physics, which thought that it was the natural tendency of things to come to rest. We can kind of see the idea in that if I have an object and I start it moving, let's say I look at this calculator moving on this board, I start this calculator moving, what does it do? Well, it eventually stops. But why does it stop? Aristotle would have said it stops because it's the natural tendency of objects to come to rest. But what Newton tells us is, no, the reason it stops is because there must be a force acting on it to change its velocity. Well, what is the force? Well, it's the friction between the calculator and the board. The friction acting on the calculator is what actually brings it to rest. Okay, very, very good. Now, what about let me give you an example now. So this gives us an idea of why it's so important to wear a seatbelt when you're driving in a car or when you're in a car. if the car is moving along and you are not wearing a seatbelt, and if the car stops suddenly, if the car hits something and it hits the car in front of it or something, what's going to happen? Well, unless the person is buckled in, they are going to keep moving at a constant velocity in a straight line, which means they are going to continue moving forward. You want to have that seatbelt on or an airbag so that there will be a force applied to the person to slow them down, to stop them. So that's why it's important to wear seatbelts and have airbags and things like that, because if the car were to stop suddenly, you need some force in order to stop the motion of the person. Okay, very, very good. So let's keep that in mind, that if there's no net force, we maintain a constant velocity. If there is a net force, the velocity changes. Well, when velocities change, what does that give us? That gives us an acceleration. An acceleration, remember, we get from a changing velocity. So what's the relationship between the net force and the changing velocity, the acceleration? Well, that's the topic of Newton's second law. Newton's second law is probably going to be the most important equation that we are going to see all semester. And we're going to be using it in some form or another, basically for the rest of the course. Newton's second law is stated extremely simply. It doesn't have another name because the other name would be longer than the law itself. Newton's second law basically states, or it doesn't basically state, it does state, F equals ma. Now let's take a look at this. What does this mean? First of all, what is F? We have to keep in mind, F is not just any force acting on an object. F, in this case, means the net force. So when we're looking at the motion of an object, F from Newton's second law is the total vector force acting on that object, the net force. Now, typically we won't necessarily always write F net in that equation, but we do have to remember that that F is the net force, the total force. A, what's that? Well, it's the same A that we were using before. A is the acceleration. And M, what's M? M is the mass of the object. A very, very basic idea, but something that we have to keep in mind, is that when we are applying F equals ma, we have to have a particular object in mind. By object, I mean a particular physical thing. What thing, what object are we using to apply Newton's laws? We're applying Newton's laws for the object to try and solve the motion of the object. For example, if I'm talking about the motion of this apple, we need to look at the forces on the apple. Okay? We need to know what are the forces on the apple, what's the net force on the apple, what's the mass of the apple, what's the acceleration of the apple, and that's what is going to be involved in Newton's second law. So keep in mind, anytime you want to apply Newton's second law, or any of these laws, you've got to have a particular physical object in mind, and we're then going to be applying our equations of motion, our Newton's laws, things like that, on that particular object. So maybe one of the first things you have to do when thinking about a problem is to decide what's the object in this problem that I'm going to be thinking about and apply these equations to. Okay, now we've talked a lot about acceleration. What about mass? What is this thing, mass? Mass is a measure of how much stuff a particular object has, so to speak. I mean, that's a very, very qualitative idea, but it's good enough for us at the moment. Usually, often people think of mass and weight as synonymous, as meaning the same thing, but they are not. We'll see what the difference is later on, but for now, just think of mass as how much stuff something has. This apple, I can feel, has a certain amount of heft to it, qualitatively speaking. It has a certain weight, I'll just use that for the moment. I can feel the weight. If I try to pick up my coffee cup, oh, that has a little bit more. It's got more weight to it. If I try to pick up something heavier, oh, this board I was using before, that has a little bit more. So I can feel that has a little bit more mass to it. So think of mass as just how much material something is made of. Now, some things have more material packed into a smaller space. For example, you can hear it. This thing, which is made of metal, has more mass. I can feel that it's got more stuff in it, so to speak. So just think of mass as how much stuff something is made of. Often larger things have more mass, but just because something is large doesn't mean it has more mass to it. This big area of air is very large, but it doesn't have a lot of mass. There's not as much stuff in it. Okay, so qualitatively, let's just keep that in mind. The units that we will use for mass are kilograms. The standard SI unit for mass is the kilogram. Whenever I write something in square brackets, so when I write something in square brackets, what I mean is the units of that quantity. So the units of mass, the standard SI unit for mass is the kilogram. In other words, 1,000 grams. The shorthand symbol for a kilogram is kg. Now that's going to be the standard SI unit that we will use. Sometimes problems will have masses given in grams. Then typically you'll want to convert it to kilograms. Maybe it'll be in a smaller unit like milligrams or micrograms or something like that. Well, you'll often want to eventually convert it back to kilograms. So, sometimes. You won't always have to, but sometimes you'll want to. You might have something that has a very, very large mass and have it listed in, given in megagrams. And so again, you might need to convert it back to kilograms. Okay, great. So what about the units of force? Well, the units of force we can actually get from this equation, F equals ma. The units of force will be equal to the units of mass, because the units on one side have to be the same as the units on the other side. The units of force will be equal to the units of mass times the units of acceleration. Well, what are the units of mass? Kilograms. What are the units of acceleration? Well, what units have we been using in kinematics? Meters per second squared. Meters per second squared. So the units of force will be a kilogram meter per second squared. Now that combination of units is something that we are going to see so often that it's got its own name. 1 kilogram meter per second squared is called 1 Newton. 1 Newton. And we will write that as 1 capital N for short. So the units that we will typically use for force will be newtons. If we have a very small force, we might write it as a millinewton or a micronewton. If we have a very large force, we might write it as a kilonewton or a meganewton, something like that. But typically, they will be always some form of a newton. Now, keep in mind, any time you want to write a force, always make sure that you put those units for the force in newtons, or some form of newtons, millinewtons, meganewtons, something like that. Don't leave your units of force as a kilogram meter per second squared. Always write it in the standard SI unit, or a form of that, milli, mega, micro, something like that. All right, very, very good. So there we go. Those are the new units that we will be using for a force. Now, let's keep in mind that Newton's second law is what kind of equation? It is a vector equation. Now, what does that mean? Well, that tells us a couple of very important things. First of all, let's remember, what does it mean when we multiply a scalar times a vector? when we multiply a scalar times a vector, we get another vector that's in the same direction as the original vector. Well, if F is then equal to m times a, that tells us that the force vector must be in the same direction as the acceleration vector. So, for the direction, we know that F is in the same direction as A. When we apply a force on an object, it's going to accelerate in the same direction as the force. Well, that kind of makes sense qualitatively. So if I push on this apple that way, it accelerates that way. If I push on it this way, it accelerates this way. We've got to be careful and remember that this is telling us the direction of the acceleration, not the direction of the velocity. So, if I throw the ball and the apple, and this apple is moving this way, but gravity pulls it this way, it will accelerate downward. Now, that does not mean the velocity is downward. It means the acceleration is downward. So, keep in mind, the force is in the direction of the acceleration, not the direction of the velocity. Let me give you another example. For example, if, say, this apple is moving this way and I push on it this way, to slow it down, in that case, my force is in the opposite direction to the velocity. But it's in the direction of the acceleration. Remember, when something is slowing down, what direction is the acceleration? It's opposite the velocity. So, the force, the net force, is in the direction of the acceleration, which is not necessarily the direction of the velocity. It could be in the same direction as the velocity. If I were to drop this apple, the acceleration is in the same direction as the velocity, but it could be opposite the direction of the velocity. If I toss this upward, as it's slowing down, the velocity is up, but the acceleration is down. So the acceleration could be in the same direction as the velocity, opposite the velocity, it could be perpendicular to the velocity. It doesn't have any necessary correlation. It could be in any orientation, but the acceleration is in the same direction as the net force. Remember, this force is the net force, the total force acting on the object. So that tells us the direction that this equation is giving us. What about the magnitude? Well, we can just take the vector signs off to think about the magnitude. We know that F equals ma in terms of the magnitude. So the magnitude of the acceleration times the mass gives us the magnitude of the net force. Or we can also break this down into components. As a vector equation, we can look at this in terms of the x component, the y component, or even the z component if we were in 3 dimensions. So we can say that F sub x, what is that? That's the x component of the net force. And what is the x component of a sum of vectors? It's the sum of the x components. So, to find the x component of the net force, add up all the x components of all of the individual forces that are acting on something, and that must equal max, m times the x component of the acceleration. Fy, the y component of the net force, equals may, and F sub z, the z component of the net force, equals maz. So there are all sorts of parts of this equation that we can use, from the direction and the magnitude and the components, to solve a problem. All right, excellent. Let's take a look at a particular problem. Let's stick some numbers in here.